All right, welcome everyone. Today we're going to pull back the curtain on a system that's working hard in your home right now, but you've probably never seen it. We're talking about the plumbing vent system. It's the unsung hero that keeps everything flowing quietly and efficiently, and the engineering behind it is actually pretty brilliant.
So, here's how we're going to break it down. First, we'll look at the big problem these vents are designed to solve. Then, we'll get into how this whole breathing system actually works. After that, we dive into the real engineering rules, sizing, distances, and this thing called DFUs. We'll check out some advanced gear, and then we'll put it all together with a real-world design example. Let's get into it.
Okay, so first things first, let's talk about the chaos that can happen when this system is missing or, it just fails. I bet a lot of us have actually experienced this and had no idea what was causing it.
Yeah, all those weird sounds, the slow draining sink, the nasty smells that seem to come from nowhere, that's not random. It's a sign of a massive pressure problem happening inside your pipes. See, when a bunch of water rushes down a drain, it acts like a piston and creates a powerful vacuum right behind it. That's called siphonage. Without something to balance that pressure, you get all those problems.
So what's the fix for that crazy pressure problem? Well, it's a really elegant piece of engineering that basically acts as the lungs for your plumbing. It lets the entire network of pipes just breathe, and that keeps everything balanced and flowing exactly how it should.
The real hero in this whole story is this simple little U-shaped pipe under your sink, the P-trap. See that little bit of water it holds? That is the only thing, and I mean the only thing, blocking gross and unhealthy sewer gases from getting into your home. It's a super simple but absolutely vital barrier that we have to protect.
And here it is. This is the whole point of a vent system. When water goes down the drain, the vent lets air get pulled in from behind it. This inflow of air breaks that vacuum we talked about, and it stops that protective water seal in the P-trap from getting sucked right down the drain. It is literally all about letting air in at the right time.
Now, building codes all over the world have a really simple rule. Every single fixture trap has to have a vent. No exceptions. To make that happen, designers have basically four main tools in their toolbox, from a basic vent for a single sink to much more complex setups for the whole house. Okay, now let's get into the nitty-gritty, the actual engineering logic. Because it's not enough to just stick a pipe in there, it has to be the right pipe in exactly the right place and the right size.
So to figure all this out, engineers use this really clever little concept called a DFU, which stands for Drainage Fixture Unit. You can just think of it as a number that rates how much of a load a fixture puts on the system. So, a bathroom sink might be just 1 DFU, but a toilet? That's way higher, maybe 4 DFUs, because it dumps a lot of water all at once. This simple number is the starting point for everything.
This is basically the playbook an engineer follows every time. First, you identify everything that needs a vent. Then you use the DFU load to calculate the right pipe size. After that, you got to check the distance from the trap to the vent and make sure the main system, the stack, can handle the grand total load. It's a straightforward process that ensures a safe design. Now, this is where it gets really important. This chart shows the critical link between the size of the vent pipe and how far it can be from the trap. A smaller 1¼ inch pipe, for example, can only be about 1½ meters away from the trap. If you go any farther than that, that siphoning vacuum can actually suck the trap dry before the vent even has a chance to help. And right here, you can see how those DFU numbers translate directly into pipe sizes. A bathroom sink or lavatory has a low DFU, so it gets a smaller 1¼ inch vent. A kitchen sink, though, especially with a garbage disposal, has a bigger load, so it needs a bigger 1½ inch vent. The logic is simple, right? A bigger load needs a bigger pipe to let more air in.
All right, now let's look at two of the more specialized players in the game. The stack vent, which is like the system's main artery, and the air admittance valve, or AAV, which is more of a special ops tool.
The stack vent is the big one. It's the main pipe that runs all the way up through the building and out the roof, letting the whole system breathe. An AAV, on the other hand, is a cool little mechanical device. It's a one-way valve that lets air in when there's negative pressure, but it won't let any sewer gas out. It's a great problem solver for tricky spots like a kitchen island, but, and this is critical, it can never replace the main stack vent. Okay, theory is great, but let's put it into practice. We're going to walk through a quick, real-world example to see exactly how all these rules come together. So here's our job. We need to spec out the vent for a standard bathroom sink. We've measured it, and the trap arm, that's the horizontal pipe from the P-trap to the main stack, is 1.2 meters long. Now we just have to apply the rules we've learned and see if this design is going to work.
So, let's run down our checklist. Step 1. Identify the fixture. Yep, it's a lavatory, and it absolutely needs a vent. Step 2. Determine the size. We know its DFU value means it needs a minimum of a 1¼ inch vent. Step 3. Check our design distance. It's 1.2 meters. So that brings us to the final, all-important question.
Is our design distance within the limits set by the code? And you can see right here, the answer is a clear yes. Our 1.2 meter trap arm is comfortably shorter than the 1.5 meter maximum allowed for the pipe size we need. So our design checks out. It passes.
And there you have it. The design is compliant. This example perfectly shows how the fixture's load dictates the pipe size, and that pipe size then sets the rule for the maximum distance. It's a beautiful little system of logic that keeps everything safe, functional, and up to code.
So if you take one thing away from this, it should be this. Good plumbing isn't just about making sure water flows out. It's really about making sure air can flow in the right place, through the right size pipe, and in just the right amount to protect that crucial water seal in the trap.
You know, this whole idea of managing invisible forces like air pressure, well, it's happening all around you. It's in your heating and cooling systems. It's even in the structure of your house. Hopefully this explainer has given you a totally new appreciation for all the brilliant, elegant engineering that's hidden just behind your walls.